All right, we're about to go on a bit of a quantum detective hunt. We're going to be looking for particles that act like they belong inside a star, but are secretly hiding out inside tiny crystals right here on Earth.
I mean, it sounds like science fiction, right? You've got these particles that are mimicking the absolute extreme physics of deep space, zipping around near the speed of light, but they're hiding inside a small, solid material you could literally hold in your hand. Well, believe it or not, this is exactly what scientists have been hunting for.
So, the culprits we're looking for? They're these exotic, relativistic particles. And for decades, the only place you could hope to find them was in a gigantic particle accelerator. But a whole new frontier has opened up. Not out in space, but inside these really special quantum material.
The real turning point, the game changer, was the discovery of graphene. It's just a single layer of carbon atoms. And this was completely revolutionary because it proved that these bizarre, super-fast quasi-particles weren't just some concept on a blackboard. They could actually exist, and you could study them right inside a solid material. No giant accelerator required.
So who exactly is our elusive suspect? It's called the Weil fermion. First dreamed up way back in 1929, it's what we call a quasi-particle, basically an excitation inside a material that acts just like a fundamental particle. And its properties are, well, they're strange. It has no effective mass, and it just zips around following the laws of relativity. It is the ghost we are hunting for in the quantum machine.
Now, if you want to find a ghost, you've got to know how it's different from, the living. In any normal material, you're just dealing with run-of-the-mill electrons. They have mass, they follow the standard rules. But Weil fermions, they're the exotic cousins. They're effectively massless, and they play by the weird rules of relativity, all while they're hiding in a huge sea of ordinary electrons. And that's the real challenge, right? How in the world do you spot the ghost in the crowd? So how do you actually prove that something this exotic is really in there? For years, every attempt to pin down these Weil fermions just came up short. The clues that scientists were following, they just weren't strong enough to really make the case.
The early detective work really focused on two main clues. The first was measuring how electrical resistance changed when you put it in a magnetic field. But the results? They were always controversial. Turns out things like uneven current in the crystal could totally mimic the signal you were looking for. The second clue, measuring quantum oscillations, also led to a lot of ambiguous results. It became pretty clear a new, definitive forensic tool was desperately needed.
And this is the million-dollar question for experimental physicists. You can't just, pop a crystal under a microscope and see a Weil fermion floating around. You need to find some indirect property, a unique fingerprint that only this particle could possibly leave behind.
And this brings us to the hero of our story, a really clever and, surprisingly, a very physical technique. Instead of just looking at the usual electrical properties, these scientists decided to look at how the material itself moves. This new approach, it was going to build a much stronger case.
The new tool is called magnetostriction, and the idea is actually pretty simple, but it's incredibly powerful. You just put a material in a magnetic field, and if it has certain properties, it will physically stretch or shrink. The key insight here was that Weil fermions should cause a very specific, totally unique kind of stretching.
Okay, so here's how they set the trap. First, they picked a prime suspect material, one that was already known to host Weil fermions, a crystal called tantalum arsenide, or TaAs. They took this crystal, they stuck it in a really powerful magnetic field, and then used an incredibly sensitive device to measure any change in its length. And when I say sensitive, I mean they're looking for changes smaller than the width of a single atom. They were on the lookout for a very specific telltale sign.
And this is where the theory gives us the smoking gun. Physicists had already predicted exactly how a material with Weil fermions should behave differently from a normal one. It all comes down to what happens when you crank that magnetic field way up.
So here's the key difference that theory predicted. In a normal material, as you ramp up a magnetic field, the stretching effect eventually just hits a wall. It saturates. But for a material with Weil fermions, the theory said the stretching would just keep going and going and going in a perfect, straight, linear line, no matter how strong you made that field. And the theory predicted that this unique linear behavior, it would become absolutely undeniable once the magnetic field hit what's called the ultra-quantum limit. For this specific crystal, that limit was about 8 Tesla. Now, To give you some perspective on that, that's way more powerful than the magnets in an MRI machine and over 160,000 times stronger than the Earth's own magnetic field.
And bingo! The experiment worked perfectly. As soon as that magnetic field climbed past 8 Tesla, the data showed the crystal's length was changing in that exact, non-saturating, perfectly linear way. This was it. This was the unique fingerprint that only the Weyl fermions could possibly produce.
The researchers themselves said it best. This quote from their paper is basically the final verdict. That linear stretching isn't just a clue, it's a clear hallmark. It's definitive evidence for the existence of Weyl electrons in the material. Case closed. Or is it? As it so often happens in quantum physics, you solve one mystery and you just uncover another one that's even stranger. The scientists decided, hey, let's measure the crystal from a different angle. And what they found was, well, it was just astonishing.
This is where the results went from definitive to just plain bizarre. Okay, so along the crystal's main axis, the stretching was stable, predictable, just like they thought. But from the side, the effect became wildly sensitive. I mean, tilting the magnet by a single tiny degree was enough to flip the entire result from a large stretch into a large contraction. That's an absolutely incredible, dramatic response to such a microscopic change.
So, we found our ghost particle, and we discovered it lives in a very, very sensitive house. What does this all mean? Why does this discovery matter beyond just some cool fundamental physics?
So what's the bottom line here? Well, scientists now have a new, super reliable tool, a hallmark for finding Weyl fermions. And what makes magnetostriction so powerful is that it can find the ghost in the crowd. It can detect these particles even when they're totally swamped by conventional ones. And this finally gives researchers a definitive way to identify and really understand this whole new class of amazing quantum materials.
And where does this all lead? Well, being able to reliably find and understand these materials opens the door to actually using their strange properties. This could launch a whole new field of wildtronics, creating next-generation quantum devices that run on the bizarre, relativistic nature of these ghost particles.
And that's really the thought I want to leave you with. We've gone from a 90-year-old prediction to having a definitive tool in our hands. The hunt for these ghost particles might be over, but the era of actually building with them, it's just beginning. What new technologies will they help us unlock? That's the next chapter. Thanks for checking out this explainer.